In this video, we will start with Chapter 2, and in particular concept of average rate of change. Let's take a look at our first example here. I'm sure you guys have been seeing a lot of these graphs on the news lately. This is the total number of fatalities in Italy from COVID-19. I've taken the data from earlier in the year because we will be able to better to have all the available data to us. And the question is, find the average number of fatalities over the first month. Now, it is actually really useful to think about units because this might give you a hint as to what it is you're trying to compute and how to compute it. The average number of units means I would like a measure of something like the number of fatalities per day. Per is division, so what I would really like is the number of new fatalities divided by the time period in which they occurred. And that is exactly how one computes an average of any function, and this function in particular. We'll generalize the process in a little bit. So the average here is going to be the number of new fatalities over the number of total days that have surpassed. So let's just say the time during which they occurred. Now, we're going to have to take a little closer look at the graph. The number of new fatalities, so I'm computing over the first month. So I'm looking at, let's say, February 24th. It seems that that's the first recorded cases that I have. And then March 24th. Just thinking that I have about 30 days in a month. This was a leap year, so this is actually pretty close. So I'm looking at these 2 points. I need a number of total new cases in between those two. Not just the number of cases on March 24th, but the number of new cases between February 24th and March 24th, right? So I need to subtract what I had in the beginning to acquire actual new cases. Now on this graph, I don't actually have points. So if we go and take a look at where this came from, this graph is interactive. So if I can point at a point here, it will tell me exactly how many cases were recorded, how many deaths were recorded in that day due to COVID-19. So on February 24th, I have 7. On March 24th, there we go, I have 6,820. So I'm going to record those numbers on my graph. So this corresponds to 7 cases, and this corresponds to 6,820 new fatalities. Okay, so overall, over that period of time, the number of new fatalities is going to be 6,820 minus 7 divided by the number of days, which is 30. And if I compute it as a decimal, I'm going to have approximately 227 deaths per day. Now I have my graph here, and so it makes sense to ask, what does that number mean in terms of the actual graph? So let's take a look at these 2 points. I took these 2 points, and on the top of my fraction, I computed the difference between those 2 numbers, right? Between the y-coordinate of this point and the y-coordinate of this point. So I've actually computed this distance. This was my numerator in my function here, in my fraction here. And I divided by 30, which was, of course, the number of days in between those 2 points. So what I've actually done is compute rise over run, and I've come up with this number, 227. Now, rise over run always describes the slope of a line between the 2 points, which means that 227 corresponds to the slope of the line connecting these 2 points together. It is approximately 227. Okay? So now let's take a look at how we can extend this further. I've now computed an average over the first month. What happens over the second and third month? I encourage you to pause the video here and actually compute those numbers for yourself. I will just label the graph with the actual statistics for it. So on February 27th, we had 7 cases. On March 24th, we had 6,820. On April 24th, we had 25,969. And then on May 24th, 32,785. Now, before you go computing things, I would also like to point out that whenever somebody labels the graph, I strongly encourage you to actually check the scale. right? So look at my numbers here, 25,000, and that's just 25,969, right? And that occurs just about right after 25,000, which means that my scale is pretty reasonable, right? So that you didn't accidentally misplace this number with respect to your grid. Okay, so take a minute here and go and compute the average for the second and the third month, which means slope of lines here and here. Okay, so I will just give you the actual numbers. Over second month, I got month, not moth. I got approximately 638 deaths per day, and average over third month came out to be approximately 227 deaths per day. Okay, and let's once again go ahead and actually graph what that means in terms of lines on your graph here. So my first line was over the first month. I computed the slope was approximately 221 to 27. The second one, if I connect the 2 points, I can see that the slope is much steeper, which really means that the disease was spreading much faster at that point. And my average here, or the slope, came out to be 638. And then finally, the slope of the third month is more shallow again, and my number here is 227 once again. Okay, so once again, these slopes also give us some idea of how fast the disease was spreading, and the numbers should correspond to what the graph looks like, how steep the graph looks, right? So here the slope was 227 and the graph appears fairly shallow. The next slope is 638, so the number is much bigger than the previous one, and the graph appears to be going up much steeper before returning to once again a more shallow 227 slope as opposed to 638. Okay, and this will help us answer the next question too. Describe the rate of growth of fatalities over time. Is it slowing down? Is it speeding up? Is it moving at the same speed? So looking at our previously computed numbers here, I can see that at the beginning my average monthly rates were fairly shallow, and then they really spiked before coming down again. Now so based on this graph, I would say that the disease was at first fairly slow and then sped up and then slowed down again. But the one problem with averages is that you have to decide how far the 2 points that you're going to compute in between will be. So here we're computing monthly averages, which means we're taking 30 days between the 2 points. And when the disease was spreading, 30 days was a fairly long period of time. If you shorten the amount of days in between your 2 points, you're going to get better measurement of what an average is and better description of your graph. Because look, for example, here, this slope, a lot of things happened. First it was really slow and then it picked up, but it's all described with just one line. If I decide to compute averages between 2 points that are a bit closer to each other, I'm going to construct a bunch of lines between points that are approximately, let's say, a week in between, because this would have been about a month, right? So if I just continue connecting my 2 points with lines, I can see that I actually am able to follow the shape of the curve much better, which means that my averages are much better describing what was actually happening with the disease, right? So, however, this still actually ends up with the same conclusion, is that in the very, very beginning, the disease was fairly slow, and then it was really growing fast before slowing down again. This is, of course, due to quarantine and other measures. And then the next question, when are the cases growing fastest? So fastest means the highest average. And again, it depends on how far apart are your 2 points for the average that you're taking, right? Now that I have them a little closer together, we can see that probably the highest slope or the steepest line that I drew was like somewhere around here. So the second half of March. Now, of course, this is just a complete approximation of what's happening. I'm not even plugging in numbers, but this should be good enough to give you some idea of where that happens. So let me just make sure that we write this down. So the cases growing fastest, this is analogous to asking, when is the steepest slope? When is the highest average and the steepest slope occurring? Okay, and my guess, based purely on this sketch here, is that it's somewhere in the second half of March. Now, this graph isn't the best for daily cases because I don't actually see how many happen per day. I just see the total number. But there are graphs that have that as well, right? So this is the graph for the daily new cases, and we can see that the number of cases spiked at around mid to late March. So my eyeballing approximation from the previous graph is confirmed by this other graph that is actually more useful, contains better information to answer this particular question. Let's now take a look at another example. In the previous COVID-19 example, we were given a graph of a function and purely data points along the graph, which we then had to actually look up to figure out what the numerical values of those points were. In the next example here, we're going to look at something slightly different. This experiment dates back to late 1500s, somewhere around 1590, when Galileo Galilei traveled to the Italian town of Pisa to actually drop various objects off of the Leaning Tower of Pisa. Leaning Tower of Pisa was very convenient to drop things off of, so what he wanted to experiment with is dropping different weight objects or objects of different weights and seeing if they reach the ground at approximately the same time or not. So he had a collection of lead balls, all spherical, all of different weights, but approximately the same shape, and dropped them off the Tower of Pisa. They did reach the ground at the same time, and he hypothesized that acceleration due to gravity does not depend on the object's mass. And this actually laid some foundations for space exploration. One of the first astronauts in space actually brought a hammer and a feather to drop on the surface of the moon to further prove that Galileo's principle holds on the moon as well. Now, first of all, I encourage you to actually Google for that video of Apollo 11, I believe, astronauts dropping a hammer and a feather on the surface of the moon and how it reaches the actual surface at the same time. We don't expect that kind of thing to happen on Earth, and that is because the feather has a much higher surface area, which means that it is prone to air resistance, which exists on Earth, but there's no atmosphere on the moon, so there's no air resistance on the moon. Now, a variety of experiments have also allowed us to come up with formulas that describe how objects fall or how gravity actually affects all the objects, and we will derive these formulas later in the course, but now we're just going to use them. So let's take a look here. Consider a watermelon, because if you're going to drop something off the Leaning Tower of Pisa, why not a watermelon? And it's being thrown off the 55-meter Tower of Pisa. The height of watermelon from the ground t seconds after the fall is described by this formula. So as opposed to last example where we had a graph, in this example we actually have an analytical formula for it. What we would like to do is estimate watermelon's velocity in 3 seconds. First of all, let's spend a minute trying to really understand what this function is describing. It's the height of the watermelon from the ground t seconds after the fall. So as you're standing on top of the Tower of Pisa and you're dropping the watermelon down, the closer to the ground it is, the more time has passed. That function will describe, so for example here, let's say this has been 1 second into the fall, the function will describe the height of that object 1 second after the fall. Okay? Let's plug in some numbers just to sort of see how this function would work. So let's say I would like to compute h of 0 and then maybe h of 1 and let's say h of 3. Okay? So h of 0 means the height of the watermelon 0 seconds after the fall. 0 seconds after the fall means right before you actually threw it off. So based on my intuition here, right before you threw it off, the watermelon is still up here. The height of the tower is 55 meters, so I expect the number to be 55. Let's see if that's what happens. If I plug in 0 into this formula, in for t, this entire term goes away. I only have 55 left. Perfect. That confirms my intuition. Let's compute h of 1. So I plug in 1 here, compute the number. It comes out to be approximately 55 minus my computations. Oh, right. No, I can see it now. It's 50.1. Okay, so after 1 second, the watermelon is approximately 50 meters from the ground. And if I compute it at 3, so plug in 3 for t here, I should get about 10.9. I hope my numbers are correct. And these should all be in meters. Now that makes sense too, right? So as the time goes on, the watermelon gets closer and closer to the ground. So I'm expecting my numbers to be closer and closer to 0, which would be the ground level. Excellent. Now what I would like to do here is estimate watermelon's velocity in 3 seconds. Now velocity is just distance over time. So if I want to estimate the velocity in 3 seconds, I need to find the distance that it's traveled in 3 seconds over the time. But that is exactly the problem with averages. With averages, I always need 2 points to compute in between. So let's just write that down because this is kind of a key issue with averages. Average requires 2 points to compute with. So what are my 2 points going to be? If I take 0 seconds right at the start of the fall and 3 seconds right at the where I'm interested in, my time span is 3 whole seconds. That's quite a bit. So it's going to give me the average over the 3 seconds, but it's not going to give me the velocity in 3 seconds. So the closer I am to 3 seconds, the better. And you can decide on your own threshold. This is why it says estimate, because you get to pick how close to 3 seconds you're going to be. I'm going to compute the average velocity between 2.9 and 3.1 seconds. I believe that's close enough to at least provide us with some intuition about what the real velocity is going to be. Okay, so let's take a look. What would this be? Again, velocity is distance over time. I'm computing the average velocity, which means it's change in distance over the change in time. So change in distance over the change in time. And the change in distance here, I have my distance function. My distance is actually the height. So I need the change in height between these 2 points divided by the change in time. The change in height between 3.1 seconds is going to be the height in 3.1 seconds minus what the height was at 2.9 seconds divided by the change in actual time that passed. So 3.1 seconds minus 2.9 seconds. Okay? So now, the bottom, of course, is easy to compute. For the top, you're going to need to plug in 3.1 into the height function and get the number out. Same for here. You plug in 2.9 into here, compute with the whole thing, and you will get an actual number. What the overall result should be is approximately minus 29.4. It's not surprising that it's negative because we have our sort of axes pointing up from the ground, but the watermelon is coming down. What are going to be the units? So let's take a look at our computation here again. The change in distance over the change in time. The distance in this example is measured in meters. The time in this example is measured in seconds. So meters and seconds, I'm going to have meters per second. Excellent. So that's pretty fast. Whenever you have a formula like this, you can once again pick whatever 2 numbers you would like to compute in between and plug it in directly into the formula. The closer they are to the number you're interested in, the better your average will be. But once again, let's discuss what are the issues with this average? I could have picked between 2 and 4 seconds. It wouldn't have been as close. 2.9 and 3.1 is pretty close. What about 2.99 and 3.01? That's even closer still, right? What we would like to do is develop methods to actually be infinitely close to the point that we're interested in. Let's summarize this discussion of averages with one formula. So what we have before is we're computing in between two different points. So let's just make a really quick sketch to give us some geometric intuition. So the average change on the interval from A to B. So let's say this is A and this is B, and my function value at A is here, and at B, let's say here. So when I'm computing the average, all I'm computing is the change in y over the change in x. So let's write that down. Change in y over the change in x. And you probably have seen different ways to describe the exact same thing. So sometimes, or most people I bet, will be used to y2 minus 1, y1, x2 minus x1. Sometimes we use the little delta notation, so a little triangle to say the change. So the change in y over the change in x. And described purely verbally, this is really just rise over run for this function. Okay? Rise over run gives us a very clear geometric description of what is actually happening. It tells us that what this really is just an actual slope of this line. So this is a key relationship between what an average is analytically, which means that you were actually computing it as a number, and what it is on the graph, graphically. Average rate of change is the same as the slope of the secant line between the 2 points. Okay, so let's write that down. Average rate of change is the slope of the secant line between the 2 points. The 2 points that you actually chose, right? So again, like if you're computing, the closer the 2 points are, the better. Between those 2 points. The problem with averages, of course, it only describes what happens between those 2 points on average. So all I know of my function is that it goes through these 2 points. I have no idea what it looks like otherwise. So for example, my function could very well be like this, right? It goes through the 2 points, which means that the average rate of change between these 2 points on the function is described by this secant line. But my function could also look, let's say, like this. It goes through the exact same 2 points, therefore it will have the exact same average number and be described by the same secant line, but it obviously looks nothing like the red function. So what we're going to do in calculus is develop tools to better understand what happens to a function at any given point. And we will do it by essentially thinking of these 2 points traveling toward each other as close as possible, and then thinking about what the average means in that context.